Thanks for having me. Everyone, welcome to my talk, How to Build Almost Any Robot. This is really we're going to go over like a little bit of just philosophy, of my personal philosophy, a little story time of some robots that I've built in the past and like what I think about them, and then give myself a little advice to my past self. And we're going to wrap it all up with a lot more concrete, like actual robotics like knowledge, right? But if we have time at the end for some questions, I'd love to take them. Otherwise, you can find me all of tomorrow. I'm always happy to talk about robots. So let's start with, who am I and why am I up here? And that's a really great question. My name is Alex, like I said. I've been building robots for nearly a decade. Longer if you count a little bit of FTC robotics. But now I work as a senior robotics engineer at an assistive robotics company. So we build like robot wheelchairs and stuff to help people out. You can see this picture down here. This is actually just from like last week. We were doing a big demo to help people achieve more mobility in their life by giving them a wheelchair that could climb up and down curbs and use robot arms. And so that's what I feel really passionate about. But what else I feel really passionate about is what I'm here for, is my YouTube channel called Every Flavor of Robot. And I'm really passionate about science communication and educating people about robotics. So, I wasn't always into robotics, okay? We actually, it took me all the way until college to really get hooked. There were a couple things that led. There were a couple stages. And the first one was just seeing things move. I think I had a class project where I had to use some Arduino code, and I had a pencil just like taped to some servo motors. And I was using like a little joystick to move that around. And something about just moving something and seeing something across the room twitch around was just so hilarious to me. I thought it was very neat. And then a little bit more into engineering school, I had a control theory class. And control theory is about doing things that are beyond human limits. Like we were pushing robotics to do stuff that like no human could do. I saw a pendulum that was balancing with a reaction wheel. So just by spinning a wheel back and forth, it was able to balance the stick in the air. And if you watch one of my YouTube videos called The Wobbler or something like that, it was where I recreated that as kind of an ode to one of the things that really got me into robotics. And then what got me really hooked was when I started to see things make changes in the world with robotics. I joined a hackathon with a couple of friends, and we built, not that chair, that's actually the one that I was showing y'all earlier, that's at work. I don't have pictures of this because it was before Google Photos started backing up my stuff. But I joined a hackathon, and we built essentially a robot, like a RC-controlled robot that you could drive a wheelchair onto. And we gave it to this kid named Brody, and he was just an absolute menace with that thing. But he really enjoyed it. And something about seeing like all of the controls, all of the power, all of the things of robotics coming together and actually changing someone's life. That moment for me really became magic. Okay, and I got hooked. I began really thinking, like, if I can make an impact positively with robotics, like, how can I maximize that impact? How can I maximize that impact across multiple people? And so I started really obsessing over this. Okay, so hypothesis number one, if solving problems for people in wheelchairs is a positive impact, then I think I need to put more people in wheelchairs. But on analysis, that's not very good. I don't think we actually need to put more people in wheelchairs. That would be, yeah, if we think about that longer, that's actually a really bad idea. So we need a new hypothesis. Now, hypothesis number two is that solving problems for each other, because that's what I was doing. They're in a wheelchair, they're just another person. But solving problems for each other is actually more positive impact in the world, and therefore, I need to make people learn about robots so that we can all solve problems for each other. Now, the problem is, the difficulty is that robotics is a very interconnected field. And so instead of just teaching them one thing, unfortunately, to learn robotics, we have to learn a lot of interconnected things. It's like a subset of like electrical engineering, mechanical engineering, computer science. You have to know like all of this, and it feels really difficult to get started. And that difficulty is what kind of drew me to trying to solve this problem. So I know that we're at Maker Faire, and y'all are probably the most susceptible group ever to this, but just bear with me. I'm going to like go through this as if y'all don't want to build robots for a second. Why would anyone want to build a robot? I think probably the most strong argument is that for any input that you give a task, any task that you want to do, if you input your effort, you're getting a multiplied output, okay? And this is very commonly talked about in the media right now because we always hear about, oh, these companies, they're putting in a little bit of money and they're building robots and they're getting out tons of money. They're like, well, it's so much money. It's an insane amount of money. But that's not the only thing that we can do with it. We just need to apply this solution, which is already proven as a cost-effective solution to multiply our efforts to get more out of it. And we can do this. For just a second, let's focus on that fact and imagine what it would be like if we applied this to different problems in our lives. We could have community gardens with automated plants. We could have education that's like personalized to each other. We could actually have a little bit of that with, ChatGPT. We have environmental cleanup. Someone was just talking in my booth today, came up to me and was like, what if we built a robot that would just like take out these invasive species of fish? That's the type of stuff that I want to empower people to do, okay? So I could keep going on, but yeah, y'all get the idea. The second reason why, if that didn't capture your attention, is that whether or not you are going to impact the world with robotics, you are going to live in a world that is going to be impacted by robotics. And it's important that we stay educated on this because this is a serious impact. And we need to look out for each other and know what's happening in our world. Okay, so let's get on to out of the philosophy into the first thing that I wish I knew. I'm going to start with a little story time. So the very first robot I ever built was a Lego Mindstorm Scorpion. I don't know if Lego Mindstorms are still around or if that name still is recognizable, but I built a Scorpion. I was in fifth grade. I remember there being a couple of my friends. We followed the instructions. We put it together, and we were like, sick. All right, teacher, how do we program this thing? And she looked at us, and she's like, dude, this is the Alabama public education system. I don't know how to program an arachnid, electromechanical arachnid. Like, what are we talking about? And we're like, yeah, that's fair. I'm going to, go step over here and eat some more crayons or something. And then I didn't touch a robot again until high school. Now, in high school, these are not my pictures. I can't take credit for building those robots because my robots in the FTC challenge did not look that good. It was essentially the same situation. They tossed a bunch of robot parts at me, and I played around with them with my friends, and then we looked at each other, and we're like, how do we program it? And we're like, we don't know. We got a little bit further, because now that we knew trig and calculus, no, I'm just kidding, that doesn't help. It doesn't, that didn't help any. This is what I wish someone would have told me. I wish I could have just had a mentor tell me, hey, look, robotics is really just these three things. And when I say this, if you've already read the slide, it seems very obvious. Robotics is about sensing, planning, and acting. And if you do those three things, you have a robot, okay? And what's really funny is that if you take this philosophy and you apply it to everything, you realize that a lot of things around you are already robots that you wouldn't really consider. Like your dishwasher, that's a robot. It's a dishwashing robot. Your microwave, also a robot. So going through these, like sensing is the entrance of information into a system. Okay? That sounds scary, but we all know what sensors are. So you're just inputting information, and that's going to come up later. Planning is the manipulation of that information. That sounds like that's a lot of rhyming syllables, but it's like what we do with that info. And then acting is the part where the robot does robot stuff, right? So I wanted to point out that this division, I wish I would have had this even early in college. I still didn't have this, and I was still thinking about robotics as a division of like, okay, we have electrical stuff, we have mechanical stuff, and we have computer science stuff. And really, it's much more helpful if you're trying to learn about this to think about it in these groupings because all of those fields are going to be tied together, okay? Now, in college, I studied mechanical engineering. And I got to build a lot of Arduino projects, and we started doing quadcopters because I liked racing. I joined a robotic mining team, which was really cool. I did a bunch of hackathons, research projects, and a rocketry group. So I got a lot of experience with robots in college. But the robotic mining team taught me a very unique lesson. you see, this team project wasn't mining on Earth. Well, it was literally mining on Earth because I'm not an astronaut, but we were doing it in a simulated lunar environment. And what that meant is that like they had a bunch of like fake moon dust, which kind of felt like all-purpose flour mixed with sand, and it looked like concrete powder. So I don't know. But the interesting part about it is that it was really, really difficult to drive in. So if you had a robot that was trying to drive, you would get scored on how well you traversed that environment and how well you could mine gravel, pick out the gravel pieces from it, okay? Now, I got to witness 2 different competitions. It was actually competition 1, and then the president of the United States canceled the government for the second one, and then the third one I got to go to again, where we built a really beautiful robot. It was actually very interesting because the first time that we joined, the most trash robot you've ever seen. I don't think NASA's ever seen a worse robot than what we rolled into the competition with. It was more zip-tied than machine, okay? Duct tape wheels. It was like aluminum wheels wrapped in duct tape because we thought that gave us more surface area to drive. And we were really embarrassed to show it. Like, we rolled up and we're like, don't look at this. The tarp's over it because we're scared of rain, not for any other reason. And what's interesting is that whenever we tested this robot, it drove around the course like it was Lightning McQueen racing for the Piston Cup. I mean, this was a really great robot, even though it looked terrible. And to our surprise, the second time that we brought the robot, which was an immaculately designed machine, precision made, every system exactly how we drew it up, drove 2 feet and 3 inches exactly, and stalled out, got stuck in the dust. That felt wrong. I felt like something was wrong. Something didn't make any sense. And so what I wish I could tell myself is that it doesn't matter how well you implement a feature. If you're building a robot system, it doesn't matter if everything that you did at 100% accuracy. It really matters what you're actually doing. Because if you're building the wrong feature, it's wasted effort anyways. And the second thing was that you need to analyze your success as well. The reason why we developed the wrong feature for the second robot was because we never figured out why the first robot with duct tape wheels and a hacksawed together frame drove so well. Whenever we actually did the analysis, we figured out it's because the first robot was so bendy, it actually had a built-in suspension just by accident. And the second one was so rigid that as soon as it needed to flex, it just couldn't. So what the lesson was really interesting is that if you're relying on an accidental success, it's just as bad as overlooking like a failure, right? So yeah, that was a big lesson for me. Now, after building enough robots, I started to realize there's a bunch of steps that I keep repeating. I keep building these robots. I keep doing the same 5 things. I keep putting some kind of wireless communications on it. I keep designing a power stage so that I could plug into batteries. I keep adding sensors to it, and I keep adding motors to it so I can drive. And then I lost what the 5th one is while I'm up here on stage, but I'm sure there's a 5th one. And essentially, I decided to make a sense, plan, act, like just total control board. So like one circuit board that could do all 3 of the pieces of a robot. And it may not do it for every single robot, but it could do it for a lot of the robots that I wanted to build at the time. And I called that the Motor Go, because I wanted to make motors go. Now we launched a small Kickstarter, and I used some of that money to keep designing more and more boards, and prototyping and exploring different ways to make robot projects easier. We tried dual brushless motors. We tried some that fit on top of a Pi, like a Raspberry Pi hat. I started integrating servo projects. So like that's where the Etch-a-Sketch came in, because we were like, wow, we have really good fast motor controls. How do we show everyone that we can drive them to exactly the position that we're trying to? And we built an Etch-a-Sketch. And then everyone asked us, why did we not use stepper motors for the Etch-a-Sketch? Well, the one thing that we kept finding as we were collecting feedback on designing these robot platforms over and over again that surprised me is that people were really coming back to us and saying that we're learning so much, by trying many, many, many different things instead of building one really complicated robot. And this makes sense in retrospect, but at the time, I was still under the concept that like I need to build the most complicated thing ever, and that's how I'll push myself to grow. But really, what I think the lesson that I learned here is that we need to prioritize fast failures over a really, really big project, okay? And it's actually this intentional learning process, figuring out like, okay, I'm going to make a very small change to something that already works. We're going to take one smallest step in the right direction, and then we have a little bit closer to our real goal. So, something else I wanted to point out that I learned from the Motor Go stuff is that there's challenges just across the board. It's like not only are the students having trouble learning robotics because there's a lot to learn, but the educators are having trouble teaching robotics because there's a lot to teach. And if you're a company trying to build robot tools for either your actual use or education or anything like that, it's a nightmare to navigate that as well. So the light at the end of the tunnel is if you're ever feeling overwhelmed trying to learn robotics, so is everyone else. So it's like come together and feel that pain together. So just a recap of like kind of the lessons I wanted to point out before we go a bit deeper is number one is that every robot is three things. And if we keep that in mind, they don't have to feel so overwhelming. We have sense, plan, act. Lesson two is make sure that you're building the right thing. Okay? It doesn't matter how well you've done it if it was the wrong thing. Lesson three, you need to analyze your successes as well. If something works, but you didn't know how it worked, you need to figure out how it works. Lesson four is that you should be taking very small incremental steps very intentionally. That way you're learning the most effectively. And generally you also feel a lot better whenever your stuff is like constantly like working and you're getting stuff done. It feels really bad to start a really long project and get stuck in the weeds. And now, I'm going to get into some even more nerdier talk about building robots, okay? We're going to dive in to the framework of sense, plan, act, because this is like your North Star for building any robot. Break all of your problems down into these three buckets, and it will help you like not only design it, but for your educational journey as well. You're going to find that these three groups have their own design languages, their own common problems, and their own like kind of flavors of working with them. And what's really nice is if you find that your project isn't pushing the bounds on one of these, like if you're not trying to sense something that no one's ever sensed before, or you're not trying to plan in a way that no one's ever planned before, or act in a way that no one's ever tried to act before, your problem's going to be really easy because there's a lot of people working on this stuff, and we can all just kind of like take each other's work. So usually, you'll start with a project and find one step in one of these axes, and that's how you know it's a well-spec'd project. Okay, so let's talk about sensing specifically. Sensing is the input of information, and because we're dealing with computers, every single bit of information has to turn into a voltage. In one way or another, it's going to turn into a voltage. And everything is about converting things into a good voltage specifically. So here's like my very down-to-earth advice on if you're trying to add sensing to a project. These are the questions that you should ask. The first thing is you should ask, all right, what sensors exist to detect the signal that I'm trying to detect? If it's a temperature signal, like how many different ways can I detect temperature? How many of these solutions are already kind of packaged up? I can just grab this off the shelf and plug it in, and we're good to go. The second question that we need to ask is, what is the swing? If I'm trying to measure temperature in my room of 50 degrees, how much voltage change does that output? Or does the sensor handle it all, and maybe the sensor's like already taking care of this for you, and you're just talking to another computer? That's kind of a binary level of voltage swing. But you need to figure out like how high is the sensor going to go when at your maximum? And the third question is, how shaky is that data? Okay? If you can read only a little bit of swing, but your sensor value is vibrating so much that you can't tell whether or not it's high or low, then that sensor data is not good. And we actually have a word for this called your signal to noise ratio. Okay? So we're going to have I broke this up into like kind of different ways that sensors convert everything into a voltage. So some sensors are going to be direct voltage, like whenever a diode gets hit by a photon, it just generates a voltage, and that's just from the physics. That's just really cool. Whenever a quartz crystal is like compressed, you actually get a voltage out of it. That's like piezoelectric stuff, and that's just direct voltage. They might be really small, and you might have to amplify them, but they're just generating a voltage. The second one is like you're creating a current, and then you need to convert that current to a voltage. And the third one would be probably like everything else. There's some interesting things that you can find that generate different signals, and people find really creative ways to turn those into voltages. But beyond it all, you just need to keep in mind that signal-to-noise ratio is everything that you're looking for in sensing. And if you're ever having trouble figuring out like why I feel like my planning is right, my actuators do what they want, but I just can't solve this problem, you need to look if you have enough sensor resolution to do this. All right. That was really nerdy. All right, let's talk about ACT, the ACT part of the robot, and then we'll go to plan. I know that was the middle one, but I switched them around. So the good news is that right now, most robotics projects are all just electric motors. And so you have to learn about them, and there's different types, but at the core fundamental of it, they're all like the same physics. You're just generating some kind of energy out, some kind of physical work, some energy output from your electrical energy, okay? And this is really important to keep in mind, that you're never going to break any like conservation of energy, okay? So however much energy you put into your motors, that is the maximum energy that you can expect to get out of your motors. There's equations to like figure out how to calculate these things, but I don't think everyone would leave if I started talking about those. But you need to know about motors, and you need to know about that. Oh, sorry. You need to know about motors, and you need to like keep in mind that while it's really easy to get caught up in, okay, everyone's using brushless motors, everyone's using field-oriented control, there's going to be so many words, so many buzzwords that are thrown at you when you start looking at motors. Remember our lesson number 2, I think, about don't get caught up implementing the complex feature if that's not what you need. It's perfectly fine to use stepper motors when you only need stepper motors. Brush motors are a fine solution. You don't need everything to be brushless. So just honestly build with what you have available and what you have an intuition for. Now here's the catch, is that building an intuition for motors is really difficult. You can calculate everything if you have the knowledge you have a textbook on motors. The problem is, even if you know all of the equations for motors, you're not always going to have the specifications from whoever you're buying the motor from to actually input into those equations. So I wasted a ton of time trying to calculate everything about motors, only to learn that only applies if you're spending thousands of dollars per actuator. So what I recommend for any maker is that you need to just buy some motors, throw out your presentation. You need to buy some motors, get some practice playing with them, and build up an intuition for how to use them, what they can do and what they can't. Computer, please. All right. So how do we build motor intuition? This is really hard. I spent most of college picking the wrong motors, okay? And what I would tell myself if I was going back and starting over is that the first thing you need to do is find some mentors. Find someone who's used that type of motor before and be like, hey, just a gut check. Do you think I can do this, use this motor to do this? And they're going to be like, yeah. Or they're going to be like, every time I did something like that, it caught on fire. And that's a good indication that you shouldn't. The second guess that I have to give you is that thermodynamics, like I said, you're never going to get more power out of your motor than the power that you're putting into it. And spoiler alert, you're actually not even ever going to get as much power as you put into your motor, because some of it's going to be lost in efficiency. And the third thing that I can say about building your motor intuition is that, again, many small experiments are going to build up a lot faster than trying to do everything right the exact first time. So work really hard to make sure your mental model of actuators is really good, because this is like just the only relevant thing in controlling a robot, okay? Where's the flow of energy? Where is it breaking down? Where is your mental model breaking down? Okay, next slide. Now, this is a slide about both sensing and actuation. We have linearity, which is a word that just means that like things go in a line. And unfortunately with sensor data, very rarely is the sensor data that you want going to be in a perfect line, which is really confusing because it's going to make your calculations a lot harder if it's 50% more towards what you want, but it's only showing 20% higher signal. I don't know if this is losing everyone, but if you're unfamiliar with the words, linearization and discontinuous, meaning that there's like jumps in your signals, this stuff is going to be a big pain in the butt. So get some practice with that. And then we'll jump to planning, okay? So planning is the bridge between your sensors and your actuators, right? So planning is probably the most abstract because it's like, what does this even mean? In robotics words, we say that planning is the manipulation of state. And state in robotics is like everything that you know about your robot right now. Like that's the current state. Where is it at? Where is it going? Cotton Eye Joe joke. The thing that really threw me for a loop is that planning can look very, very, very different. So a very simple planner, and actually probably the most useful planner that everyone in this room can learn about, is called a PID loop. It stands for proportional, integral, derivative. There's 1,001 YouTube videos describing this very well. I have a couple of them. Shameless plug. And it operates very predictably. It's actually like you can derive them from math equations if you're a nerd. And what's really great is they happen really, really quickly, really, really reliably. So most of robotics, even today, even the most advanced robotics you see, is kind of very parallel to PID controllers. Then you have kind of the new, upcoming, the complex. These controls, these type of planning, words like inverse kinematics, which is where you know where your end of your robot needs to be, and you have to solve like where should all of my joints be to get there. Path planning algorithms, if you're like trying to solve a maze or you're trying to drive, say, a car through a street. Machine learning modules, doing machine learning stuff, which is basically juicing the most out of our signal to noise ratio. Those type of plans are very complicated and they happen much, much, much slower than anything deterministic, okay? So in both of them, the biggest complexity that you need to be aware of if you're trying to learn a lot about planning is that you need to control what roboticists call dimensionality explosion, which sounds really complicated, but it's kind of just saying like for all of the different difficulties that we have, all of the different joint positions that we have, if we need to determine like 3 calculations for every single joint and we have 30 joints because we're building a robot scorpion, that math adds up really quick. And the sooner that we can pare down our decisions and stay in the more deterministic phases of our planning, the faster our planners will be. Okay, that's a lot about planners. We're going to go on. One more problem with planning is that because these happen at 2 very different time scales, some of them are doing really, really, really slow stuff, like figuring out how to solve a maze, and other ones are just figuring out what voltage do I give the motor. This change in time is very confusing to work with, and you're going to run into difficulties with your deterministic stuff happening at the microsecond level, and then your complex stuff happening at the seconds to 10 seconds level. And we have a term that, if you're working in Arduino, is fun to learn about. It's called a real-time operating system that helps us kind of bridge that gap and make timing guarantees. Oh my goodness. We're getting to the end of the talk. I just want to talk about the final boss, and we call this integration heck. The challenge of actually combining all of this plan, sense, and act is where things are going to break down. The boundaries between these, whenever you have bad sensor data that then throws your planner for an absolute loop, and then that planner tells your motors to freak out because they don't know what they're planning, That's where robots get really, really frustrating. And understanding the handoffs between these different levels is what you need to focus on if you feel like you already have a good grasp on planning, sensing, and acting. And now, I just wanted to bring one last review slide here. The first thing that I brought y'all guys is to use the framework, sense, plan, and act. The second thing that I recommend is that you really build small and experiment very intentionally. Third is analyze both your successes, not just your failures, or analyze both your successes and your failures. 4, please stay curious. Never just sweep things under the rug. Ask why. It's going to build up over time. And then 5 is for any project you're thinking about building, you need to make sure that there's only one thing that you're trying to learn at a time. Otherwise, robotics is going to get really complicated really fast. And if you like building robots, you want to build almost anything with us, you could join my Discord server. We have a whole community of roboticists that are always online shooting each other messages, brainstorming with each other. We run design challenges. We build, all of the mission that we're doing at Every Flavor Robotics is right here on this Discord server. So thank you guys so much for having me. And I hope that was a acceptable amount of complexity and thank you.
So what got you into robotics?
Yeah, I mean, what really got me into robotics was kind of just a continuous accidental bumping into it. And every time that I bumped into the robotics problems, I kept noticing, like, there's just so many questions to ask. There's so much interconnectivity between the fields that it always felt like a really big puzzle. And that really got me going. And then finally, when I saw things actually move as a prize for solving that puzzle, I was hooked.
My son is a graduate student at FIU, and he's studying robotics engineering. What would you recommend him to do? Like, he's doing this online, when he graduates, to help him find a job, to make connections. Do you have any advice?
I would say that robotics as a field really values people who have built things with their hands, right? So in grad school, it's unique that you get to solve a lot of problems that have never been solved. You're really pushing the bounds of that sense, plan, or act. You're usually choosing one of those, and you're becoming the leading expert in that subfield. But where it breaks down is that someone has to also do the work to get that cutting edge back integrated through that integration problem at the end. And so what I would recommend for anyone that has the time and the resources is to build more robots, solve problems in your community, and show that you can actually apply your problem solving to the real world, because that's what the companies are going to be, they're going to find valuable.
Any questions? No? All right, big round of applause for Every Flavor of Robot.